Early life and education of Max Planck, ladies and gentlemen. Today we begin our journey into the life of one of the most brilliant minds in the history of physics, Max Planck, the father of quantum theory. To truly understand the magnitude of his contributions, we must first step back and explore the environment, upbringing, and education that shaped the man behind the revolutionary ideas. Max Carl Ernst Ludwig Planck was born on April 23, 1858, in Kiel, Germany, a time of great scientific curiosity and political change in Europe. His family environment played a critical role in nurturing his intellectual growth. Max's father, Gustav Planck, was a law professor, while his mother, Emma Patzig, came from a family that valued education and intellectual pursuits. This combination of disciplined thinking from his father and the cultural richness from his mother created a unique atmosphere in which Max could thrive. From a very young age, he was immersed in an environment that valued knowledge, discipline, and moral integrity. Planck displayed exceptional intellectual abilities early on. Unlike many prodigies who excel in one area, Max was remarkably well-rounded. He excelled not only in mathematics and physics, but also showed a deep appreciation for music and the arts. Indeed, music would remain a lifelong passion and a source of solace throughout his life, particularly during periods of personal and professional challenge. This duality of mind-scientific precision, combined with artistic sensitivity, was a hallmark of his character and would later influence the way he approached scientific problems. His formal education began at the Maximilians Gymnasium in Munich, one of the most prestigious schools in Germany at the time. The rigorous curriculum emphasized classical education, Latin, Greek, philosophy, mathematics, and the natural sciences. It was here that Planck's fascination with physics began to crystallize. He was particularly drawn to the logical beauty of mathematics and the way it could be used to describe the natural world. Unlike many students who approached studies mechanically, Planck approached learning with curiosity and deep reflection. He sought to understand the why behind every principle rather than simply memorizing formulas. During his youth, Germany was undergoing rapid scientific and industrial transformation. The study of thermodynamics, electromagnetism, and mechanics was gaining prominence, and young Planck was at the center of this intellectual awakening. His teachers quickly recognized his potential and encouraged him to pursue higher education in physics. At the age of 17, Planck entered the University of Munich, where he initially studied under the guidance of renowned physicist Gustav Kirchhoff, famous for his work in spectroscopy and electrical circuits. Kirchhoff's precise, methodical approach to physics left a lasting impression on Planck, shaping his analytical rigor. However, Planck's journey was not just shaped by the classroom. He was deeply influenced by the work of James Clerk Maxwell and Ludwig Boltzmann, whose studies in electromagnetic theory and statistical mechanics opened new horizons in understanding energy and matter. Planck was particularly inspired by the challenges posed by the problem of Blackbody radiation, a puzzle that would dominate his early career and eventually lead to his groundbreaking discovery of energy quanta. After a few years at the University of Munich, Planck transferred to the University of Berlin, where he came under the mentorship of Hermann von Helmholtz and Wilhelm Eduard Weber. These brilliant scientists exposed him to cutting-edge research and the philosophical foundations of physics. Helmholtz, in particular, instilled in Planck a respect for the interplay between theory and experiment, emphasizing that true scientific understanding comes from harmonizing mathematical predictions with observed reality. This mentorship provided Planck not only with technical knowledge, but also with a scientific world view that valued careful reasoning intellectual honesty, and humility. By the time Planck completed his doctoral studies in 1879, he had already demonstrated remarkable originality and intellectual maturity. His dissertation focused on the second law of thermodynamics, laying the groundwork for his later revolutionary work in quantum theory. What set Planck apart was his insistence on clarity, precision, and depth. Even as a young scientist, he was not satisfied with superficial explanations. He sought to understand the fundamental principles that govern nature. In reflecting on Planck's early life and education, one cannot overlook the personal qualities that shaped him. He was disciplined, methodical, and deeply committed to his work. Yet, he also possessed a rare humility and a sense of responsibility to society, understanding that scientific discoveries carry both intellectual and ethical weight. These early influences, family, mentors, and the intellectual climate of Germany, combined to create a foundation upon which Planck would build one of the most transformative contributions to science in the 20th century. In conclusion, the early life and education of Max Planck reveal a man of extraordinary intellect, curiosity, and integrity. Born into a nurturing yet rigorous environment, guided by brilliant mentors, and inspired by the scientific challenges of his era, Planck was uniquely prepared to tackle the mysteries of the universe. His early years were not just a prelude to his achievements, they were the crucible in which the foundations of quantum theory were forged. Understanding this context allows us to appreciate not just what Planck discovered, but who he was, and why his insights changed the very way we understand the world around us. Planck's work in thermodynamics and blackbody radiation, ladies and gentlemen, after exploring Max Planck's early life and education, we now turn to the scientific foundation that set the stage for his revolutionary contribution to physics, his work in thermodynamics and blackbody radiation. These fields, though seemingly technical, were the crucible in which Planck's mind confronted the limits of classical physics and ultimately led him to the birth of quantum theory. During the late 19th century, thermodynamics, the study of heat, energy, and work, was one of the most advanced areas of physics. Scientists had already formulated the laws of thermodynamics, including the famous second law, which states that entropy, or disorder, in a closed system always increases. This principle described how energy transforms and dissipates in the universe, yet many phenomena remained unexplained. Planck, deeply interested in understanding nature at its most fundamental level, was drawn to these challenges. One of the most pressing scientific problems of his time was the blackbody radiation problem. A blackbody is an idealized object that absorbs all radiation falling on it and emits energy depending on its temperature. Physicists observed that as a blackbody is heated, it emits radiation across a spectrum of wavelengths, but classical physics, based on Maxwell's equations and thermodynamic principles, could not accurately describe the intensity of this radiation at high frequencies. According to classical theory, the energy emitted should increase without bound as the frequency rose, a prediction that became known as the ultraviolet catastrophe. In short, classical laws of physics were failing spectacularly at describing reality. Planck approached this problem with extraordinary rigor and determination. He examined the relationship between energy and frequency in emitted radiation, and sought a mathematical formula that could fit experimental observations. Unlike some of his contemporaries, who were quick to dismiss discrepancies as experimental error, Planck trusted the data and committed himself to finding a theory that could reconcile theory with reality. His work in thermodynamics, particularly his understanding of energy conservation and entropy, provided the conceptual framework for approaching this puzzle. In 1900, after years of careful study, Planck proposed a mathematical formula that perfectly described the observed spectrum of blackbody radiation. But the formula alone was not enough. He sought a physical interpretation. To do so, he made a bold and unprecedented assumption. He suggested that energy could only be emitted or absorbed in discrete amounts, which he called quanta. This meant that energy was not continuous, as classical physics assumed, but quantized. Each quantum of energy was proportional to the frequency of radiation, a relationship expressed by the now famous equation E equals h nu, where E is energy, nu is frequency, and h is Planck's constant. This insight was monumental. Planck did not fully understand the broader implications at the time, and he himself regarded the concept of energy quanta as a mere mathematical trick to solve a specific problem. Yet, this small but radical idea would shake the foundations of classical physics and open the door to an entirely new understanding of the microscopic world. By applying the laws of thermodynamics in combination with his novel assumption, Planck not only solved the blackbody radiation problem, but also laid the groundwork for quantum mechanics, a theory that would dominate 20th century physics. Planck's work in thermodynamics was also critical because it linked energy transformations to statistical behavior. Inspired by Ludwig Boltzmann's statistical mechanics, Planck analyzed how energy is distributed among oscillators' tiny systems that vibrate at specific frequencies. By treating these oscillators as quantized, Planck could calculate the average energy at each frequency and successfully reproduce the experimental radiation curves. This blending of thermodynamics, statistical mechanics, and quantization was the hallmark of Planck's genius. He was able to synthesize disparate fields into a coherent solution to one of physics' most vexing problems. It is worth noting the courage required for Planck to propose quantization. At the time, classical physics, Newtonian mechanics, and Maxwell's electromagnetic theory was considered nearly complete, a flawless description of the physical world. Challenging its foundations, even indirectly, was a daring intellectual move. Planck's humility and meticulous approach allowed him to introduce a radical idea cautiously, letting the mathematics and experimental evidence speak for themselves rather than seeking immediate fame or confrontation. This methodical, evidence-based approach became a hallmark of his scientific character and inspired generations of physicists who followed. The solution to the blackbody radiation problem was not just an isolated success. It had profound implications. It demonstrated that classical concepts of energy and matter were insufficient at small scales and hinted at the probabilistic nature of the microscopic world. Planck's quantization idea became the cornerstone for later developments by Albert Einstein, Niels Bohr, and Werner Heisenberg, ultimately giving rise to the full framework of quantum mechanics. Without Planck's careful work in thermodynamics and his resolution of blackbody radiation, the revolutionary developments of the 20th century, semiconductors, lasers, nuclear energy, would have been delayed or taken a different trajectory. In conclusion, Max Planck's work in thermodynamics and blackbody radiation exemplifies the intersection of meticulous observation, mathematical precision, and bold conceptual thinking. He faced a paradox that threatened the prevailing laws of physics, yet he approached it with humility and intellectual rigor. By combining insights from thermodynamics with the revolutionary idea of energy quanta, Planck not only solved a pressing scientific problem, but also laid the foundation for an entirely new era in physics. His work reminds us that true scientific breakthroughs often emerge when courage, patience, and careful reasoning converge. a lesson as relevant today as it was in Planck's time. The revolutionary concept of energy quanta, ladies and gentlemen, having explored Max Planck's early life, education, and his work in thermodynamics and blackbody radiation, we now arrive at what is undoubtedly the most transformative aspect of his legacy, the revolutionary concept of energy quanta. This idea, simple in appearance yet profound in its implications, shattered centuries of classical physics and laid the foundation for the modern understanding of the microscopic world. To appreciate the magnitude of Planck's insight, we must first understand the context of physics at the turn of the 20th century. Classical physics, rooted in the work of Newton, Maxwell, and others, treated energy as a continuous quantity. Heat, light, and radiation were thought to flow in smooth, unbroken waves. This framework worked remarkably well for most everyday phenomena, from planetary motion to mechanical engineering. Yet there were puzzles, particularly at very high frequencies of electromagnetic radiation, where classical theories failed dramatically. The Blackbody radiation problem, which we discussed previously, was chief among them. Planck's brilliance was his ability to confront these anomalies not with dismissal or compromise, but with creative and radical thinking grounded in mathematics and evidence. In 1900, in order to solve the Blackbody radiation problem, he proposed an idea that would shock the scientific world. Energy is not continuous, but comes in discrete packets, which he called quanta. This was a departure so fundamental that even Planck himself initially regarded it as a mathematical tool rather than a literal description of nature. The essential idea of energy quanta can be expressed by the simple equation E equals h nu E equals h backslash nu E equals h nu here. E represents the energy of a single quantum, nu backslash none, U is the frequency of the associated electromagnetic wave, and hh is Planck's constant, a new fundamental constant of nature. This relationship implies that energy can only be exchanged in multiples of h, u backslash none u, no matter how small the interval. In other words, the universe has a subtle granularity at the level of energy exchange, an insight that was completely alien to classical physics. It is important to recognize why this idea was revolutionary. Up until then, physicists believed energy could be divided infinitely. Any amount of energy could exist or be transferred continuously. Planck's quanta suggested a natural limit to how energy behaves at microscopic scales. This was not merely a small correction to existing theories. It implied that classical assumptions about the smoothness and continuity of nature were fundamentally incomplete. The concept of energy quanta also had deep implications for understanding thermodynamics and statistical mechanics. Planck applied this idea to oscillators, idealized systems that absorb and emit energy at specific frequencies. By assuming these oscillators could only exchange energy in discrete packets, he could derive an exact formula for Blackbody radiation that perfectly matched experimental data. This was a triumph. A single radical assumption, carefully applied, resolved a long-standing scientific paradox. Planck's cautious personality is worth noting here. Despite the revolutionary nature of his insight, he presented it carefully, almost reluctantly, to the scientific community. He described quanta as a purely formal assumption at first, and even he did not immediately grasp that this would lead to an entirely new framework for physics. This humility underscores Planck's character. He was not seeking fame, but truth, allowing the evidence to guide interpretation rather than forcing reality into preconceived ideas. The broader consequences of the energy quantum concept became clear only in the years following Planck's initial work. Albert Einstein, in 1905, extended Planck's hypothesis to explain the photoelectric effect, showing that light itself is quantized into particles we now call photons. This directly challenged the classical wave theory of light and confirmed the revolutionary implications of Planck's work. Later, Niels Bohr would use the idea of quantized energy levels to explain atomic spectra, and the full development of quantum mechanics by Heisenberg, Schrödinger, and Dirac would rely fundamentally on the concept that energy at microscopic scales is discrete, not continuous. In essence, Planck's energy quanta were not just a solution to a single problem. They revealed a new layer of reality. They showed that at microscopic scales, nature is governed by rules that are probabilistic, discrete, and sometimes counterintuitive. What had once seemed like a solid, continuous world was, in fact, composed of tiny, indivisible packets of energy, each obeying precise mathematical laws. This shift in perspective marked the beginning of the quantum revolution, fundamentally altering how we understand the universe from the subatomic to the cosmological scale. It is also crucial to appreciate the personal dimension of Planck's contribution. He introduced an idea that would challenge the very foundation of his beloved classical physics, yet he did so with careful reasoning, humility, and an unwavering commitment to truth. His insight was not born from a desire to be radical, but from a relentless curiosity and a refusal to accept contradictions in nature. In this way, Planck exemplifies the ideal of scientific integrity, a mind courageous enough to question, disciplined enough to reason, and humble enough to let evidence guide the path forward. In conclusion, the revolutionary concept of energy quanta represents Max Planck's most profound legacy. By proposing that energy exists in discrete packets, he challenged centuries of classical thought, resolved the Blackbody radiation problem, and laid the foundation for quantum mechanics. What began as a formal assumption became a cornerstone of modern physics, influencing generations of scientists and opening doors to technologies and discoveries that continue to transform our world. Planck's insight reminds us that even the most fundamental laws of nature may hide surprises, and that true progress often comes from the courage to think differently while remaining anchored in careful observation and rigorous logic. Planck's constant in its significance, ladies and gentlemen, as we continue to explore the monumental contributions of Max Planck, we arrive at a concept that lies at the very heart of quantum mechanics, Planck's constant. This seemingly simple numerical value, denoted by HHH, is far more than just a symbol in a formula. It represents a profound shift in our understanding of nature, a bridge between the classical world and the quantum universe, and a legacy that defines the modern era of physics. To appreciate Planck's constant, we must first recall the context in which it emerged. In 1900, Planck was grappling with the problem of Blackbody radiation, the challenge of explaining how objects emit energy in the form of electromagnetic radiation based on their temperature. Classical physics predicted that the energy emitted would increase without limit as the frequency rose, a divergence that became known as the ultraviolet catastrophe. Experimental observations, however, showed a completely different pattern. The energy emission peaked at a certain frequency and then declined at higher frequencies. Planck's solution was revolutionary. He introduced the concept of energy quanta, asserting that energy could only be emitted or absorbed in discrete amounts. The proportionality constant linking energy to frequency became known as Planck's constant. Mathematically, it is expressed as E equals h nu E equals h backslash nu E equals h nu here. E is the energy of a quantum, nu backslash none U is the frequency of radiation, and hh is Planck's constant. This equation encapsulates a principle so fundamental that it underlies the behavior of all microscopic systems. Energy is not continuous, but comes in indivisible packets, and Planck's constant defines the scale of these packets. The numerical value of Planck's constant, approximately 626 times 10^3 joule seconds, may appear minuscule, but its significance is enormous. It sets the scale at which quantum effects become observable. In everyday life, where energies are large and scales are macroscopic, the discreteness implied by hh is negligible, so classical physics works exceptionally well. But at atomic and subatomic scales, Planck's constant governs phenomena in ways that are profound, counterintuitive, and experimentally verifiable. It tells us that nature has a fundamental granularity, an inherent step size, in the exchange of energy. One of the most important implications of Planck's constant is its role in defining the quantum of action, a concept central to quantum mechanics. In classical physics, action a quantity combining energy and time or momentum and position can vary continuously. Planck's constant, however, establishes that action is quantized. It can only take discrete multiples of hh. This realization formed the conceptual foundation for later developments, including Heisenberg's uncertainty principle, which limits the precision with which we can simultaneously know a particle's position and momentum. The constant thus links the abstract mathematics of quantum theory with the physical reality of microscopic systems. Planck's constant also appears in numerous critical formulas across physics. For example, in Einstein's explanation of the photoelectric effect, the energy of emitted electrons depends on the frequency of incident light multiplied by hh, confirming the particle-like nature of photons. In atomic physics, Niels Bohr used Planck's constant to quantify the allowed energy levels of electrons orbiting the nucleus, leading to accurate predictions of atomic spectra. Later, in Schrödinger's wave mechanics, hh enters as a key factor connecting wave functions to observable energies. In essence, Planck's constant is woven into the very fabric of quantum theory, linking energy, frequency, momentum, and wavelength in ways that classical physics never could. Beyond its technical importance, Planck's constant carries profound philosophical significance. It signifies the limits of classical determinism and the introduction of discreteness and probability into our understanding of nature. In a universe governed by hh, energy cannot vary infinitely smoothly. There are fundamental quanta that define the smallest possible exchanges of energy. This challenges our intuition and compels us to rethink the continuity of the natural world. Max Planck's insight thus reshaped not only physics, but also our conceptual framework for understanding reality itself. It is also worth noting the personal dimension of Planck's discovery. He arrived at hh through careful observation, meticulous calculation, and deep reflection on experimental data. Unlike a sudden flash of inspiration, this was a product of disciplined reasoning and patience. Planck himself initially viewed his constant as a mathematical convenience rather than a radical redefinition of nature. It took the subsequent work of Einstein, Bohr, and other pioneers to fully reveal the far-reaching consequences of this fundamental constant. Yet, without Planck's disciplined insight, the quantum revolution might have been delayed by decades. The significance of Planck's constant extends even beyond theoretical physics. Today, it underpins technologies that define the modern world, from semiconductors and lasers to quantum computing and medical imaging. Every time we harness light, manipulate electrons, or develop nanoscale devices, we are applying principles that flow directly from the constant that Max Planck introduced over a century ago. In this sense, HHH is not just a symbol in physics. It is a key that unlocks both the mysteries of the universe and the practical innovations that shape our daily lives. In conclusion, Planck's constant is the cornerstone of quantum physics. It transforms our understanding of energy from a smooth continuum into discrete quanta, defines the scale at which quantum effects dominate, and links abstract mathematical principles with experimental reality. Its discovery was not just a technical achievement, but a paradigm shift that forever changed how we understand the universe. Max Planck's insight into this fundamental constant exemplifies the power of careful observation, disciplined reasoning, and courageous thinking. By introducing HHH, Planck did not merely solve a scientific problem. He opened the door to an entirely new way of perceiving reality, one that continues to inspire and challenge scientists more than a century later. The birth of quantum theory and its impact on physics, ladies and gentlemen, we now reach a pivotal moment in the history of science. The birth of quantum theory, an intellectual revolution that changed our understanding of the universe forever. At the heart of this revolution stands Max Planck, whose careful study of blackbody radiation and introduction of energy, quanta, laid the foundation for a new era of physics. But quantum theory is not just a scientific breakthrough. It is a profound paradigm shift that reshaped the very principles upon which classical physics was built. In the late 19th century, classical physics reigned supreme. Newton's laws explained the motion of planets. Maxwell's equations described the behavior of electromagnetic waves, and thermodynamics offered powerful tools to understand energy and heat. Yet, as precise experiments probed deeper into nature, anomalies began to appear, phenomena that classical theory could not explain. Among these was the blackbody radiation problem, which revealed that classical predictions led to infinite energy emissions at high frequencies, a paradox famously called the ultraviolet catastrophe. It was Max Planck who first recognized that a solution required a radical departure from classical assumptions. In 1900, Planck proposed that energy is not continuous but quantized, coming in discrete units called quanta. This idea, encapsulated in the equation E equals h nu E equals h backslash nu E equals h nu, introduced the revolutionary concept that energy could only exist in specific, indivisible packets. Planck's work marked the birth of quantum theory, a framework that would ultimately describe the behavior of matter and energy at atomic and subatomic scales. The significance of this development cannot be overstated. Prior to Planck, physics was governed by deterministic laws. If one knew the position and momentum of a particle, its future behavior could, in principle, be predicted with absolute certainty. Quantum theory, however, introduced a fundamental limit to such predictability. Energy quanta implied that interactions at microscopic scales were discrete rather than continuous, and the precise outcomes of measurements could only be described probabilistically. In this sense, Planck's quantum hypothesis shattered the classical world, forcing scientists to rethink fundamental concepts of nature. The birth of quantum theory also catalyzed a wave of scientific exploration that rapidly transformed physics. Albert Einstein built upon Planck's idea in 1905, explaining the photoelectric effect by demonstrating that light itself is quantized into photons. This confirmed that Planck's quanta were not merely a mathematical trick, but a reflection of reality. Soon after, Niels Bohr applied quantization to atomic models, introducing discrete energy levels for electrons and explaining atomic spectra with unprecedented accuracy. Over the following decades, Werner Heisenberg, Erwin Schrödinger, and Paul Dirac expanded quantum mechanics into a comprehensive framework encompassing wave, particle duality, probability, and the behavior of subatomic particles. All of this was built upon the foundation laid by Max Planck. Beyond its theoretical elegance, the birth of quantum theory had profound practical implications. It explained phenomena that classical physics could not: the stability of atoms, the behavior of semiconductors, the properties of lasers, and the interaction of light and matter. Modern electronics, telecommunications, and computing. All technologies we rely on daily depend on principles rooted in Planck's quantum hypothesis. In essence, his discovery was not just an abstract theoretical insight, but a practical key that unlocked the technological revolution of the 20th and 21st centuries. The impact of quantum theory also extended to the philosophical and conceptual foundations of science. Planck's work revealed that nature is fundamentally discrete at microscopic scales, challenging the classical notions of continuity and determinism. This shift forced scientists to adopt a new way of thinking, one that blends probability with physical laws and acknowledges limits to what can be precisely known. Concepts such as Heisenberg's uncertainty principle and wave, particle duality, central pillars of modern physics, owe their existence to Planck's initial insight into quantization. It is remarkable to consider that Planck himself approached this revolutionary idea with caution. He initially viewed energy quanta as a formal device, a solution to a specific problem, rather than a universal principle of nature. Yet, the implications were far-reaching, influencing generations of physicists and transforming science in ways Planck could scarcely have imagined. This combination of intellectual courage, humility, and rigorous reasoning defines Planck's character and underscores the enduring legacy of his work. The birth of quantum theory also highlights the collaborative nature of scientific progress. While Planck laid the groundwork, subsequent scientists Einstein, Bohr, Heisenberg, Schrödinger, and many others built upon his ideas, demonstrating that groundbreaking discoveries often arise from a continuum of inquiry rather than isolated genius. Planck's contribution was the spark, the critical insight that illuminated a path toward understanding the microscopic world. Without his hypothesis of quantization, the quantum revolution might have been delayed or taken an entirely different trajectory. In conclusion, the birth of quantum theory marks one of the most profound shifts in the history of science. Max Planck, through his meticulous work on Blackbody radiation and the introduction of energy quanta, challenged the foundations of classical physics and created a new framework for understanding nature. The theory that emerged from his insights not only resolved long-standing scientific puzzles, but also enabled technological advancements that define our modern world. Beyond equations and experiments, Planck's contribution represents a triumph of intellectual courage, curiosity, and careful reasoning. A reminder that scientific progress often requires us to question even the most fundamental assumptions about reality. Max Planck's work reminds us that the universe is richer, more intricate, and more surprising than we ever imagined. By daring to think differently, he opened a door to a world where energy is quantized, matter behaves in unexpected ways, and the mysteries of the microscopic realm reveal both the limits of human knowledge and the boundless potential of scientific discovery. Planck's influence on contemporaries like Einstein, ladies and gentlemen, as we continue to explore the extraordinary legacy of Max Planck, we reach a vital aspect of his influence, the impact he had on his contemporaries and the generation of physicists who would carry the torch of the quantum revolution forward. Among these figures, none was more profoundly influenced by Planck than Albert Einstein, whose work would extend and transform the ideas Planck first introduced. Understanding this intellectual lineage reveals how one thinker can ignite a scientific revolution that reshapes human understanding. Max Planck, through his meticulous study of blackbody radiation and the introduction of energy quanta, provided a framework that challenged classical physics while remaining rooted in rigorous mathematical reasoning. At the time, many of his peers struggled to grasp the radical implications of quantized energy. Some dismissed it as a mathematical convenience. Others were skeptical of abandoning the established continuity of classical laws. Yet Planck's authority, precision, and reputation as one of the most careful theoretical physicists of his era lent enormous credibility to these revolutionary ideas. His work signaled to the scientific community that classical assumptions were no longer sufficient to describe nature at microscopic scales. Albert Einstein, then a young physicist working at the Swiss Patent Office in 1905, recognized the significance of Planck's work. While Planck had introduced energy quanta to resolve a specific problem in blackbody radiation, Einstein saw a broader implication. Light itself might be quantized, composed of discrete packets of energy, later called photons. Einstein's explanation of the photoelectric effect relied directly on Planck's hypothesis, earning him the Nobel Prize in 1921. Without Planck's careful introduction of quantization, Einstein may not have had the foundation to propose that light behaves both as a wave and as a particle. Planck's influence, therefore, extended far beyond his own research. He provided the intellectual scaffolding upon which others could construct new theories. Planck's influence was not limited to Einstein alone. Niels Bohr, who developed the Bohr model of the atom, explicitly acknowledged Planck's quantum hypothesis as a guiding principle. Bohr's revolutionary idea that electrons occupy discrete energy levels and emit or absorb energy only in quantized amounts was a direct application of Planck's work. Likewise, physicists such as Werner Heisenberg, Erwin Schrödinger, and Paul Dirac built the formal structure of quantum mechanics on the foundation Planck had established. The idea that energy is quantized permeates all of quantum theory, and its origin can be traced back to the rigorous, cautious insights of Max Planck. It is also worth noting the personal and professional example Planck set for his contemporaries. He combined scientific daring with intellectual humility, introducing radical ideas without arrogance and always grounding them in careful observation and mathematical rigor. This approach inspired trust and admiration, encouraging other scientists to explore and expand upon his ideas rather than dismissing them. Planck's demeanor as a mentor and collaborator, along with his clear commitment to truth and methodical reasoning, created an intellectual environment in which innovation could flourish. Planck's influence extended beyond theoretical developments. By demonstrating that physics could evolve in response to experimental evidence, he encouraged a generation of physicists to question established principles and embrace uncertainty when necessary. His work underscored a crucial lesson. Progress in science often comes not from clinging to tradition, but from responding creatively and rigorously to the limitations of existing theories. Einstein, Bohr, Heisenberg, and many others internalized this lesson, and it became a guiding principle for the entire quantum revolution. Another remarkable aspect of Planck's influence is how he balanced radical ideas with careful caution. He did not rush to proclaim energy quanta as a universal law. Instead, He framed it as a formal hypothesis supported by experimental evidence. This intellectual discipline allowed others, such as Einstein, to extend and generalize the concept without being constrained by Planck's initial caution. In effect, Planck created a safe yet fertile intellectual space where revolutionary ideas could be tested, refined, and ultimately embraced. Planck's influence also demonstrates the importance of intellectual dialogue in science. Through correspondence, lectures, and publications, he engaged with contemporaries, exchanging ideas and encouraging scrutiny of his work. These interactions accelerated the adoption and refinement of quantum concepts, showing that breakthroughs rarely occur in isolation. Planck's readiness to communicate his insights, coupled with his reputation for integrity and rigor, made his work a beacon for scientists navigating the new and often counterintuitive terrain of quantum phenomena. In reflecting on Planck's impact on contemporaries like Einstein, we see a vivid illustration of how scientific revolutions unfold. One brilliant mind identifies a limitation or paradox within existing theories, proposes a solution, and carefully presents it to the world. Then, inspired minds take that insight, explore its broader implications, and construct new frameworks that transform our understanding of reality. Planck's influence on Einstein, Bohr, and the entire quantum generation exemplifies this process perfectly. In conclusion, Max Planck's influence on his contemporaries was profound and multifaceted. Through his introduction of energy quanta, his methodical approach to revolutionary ideas, and his commitment to rigorous reasoning, Planck provided the foundation upon which a new generation of physicists built the edifice of quantum mechanics. His impact on Albert Einstein alone demonstrates how one scientist's insight can catalyze a cascade of discoveries that reshape the very fabric of science. Planck was not only a pioneer of quantum theory, he was a guiding force for an entire generation, showing that true innovation requires courage, discipline, and a willingness to think differently while respecting the evidence. Max Planck's legacy reminds us that breakthroughs in science are not just about individual discoveries, they are about the intellectual influence and inspiration one mind can have on others, sparking a chain reaction that propels humanity's understanding forward. Without Planck, the quantum revolution might have been delayed. With him, the 20th century witnessed a transformation in physics unlike anything in human history. Challenges and skepticism faced by Planck, ladies and gentlemen, as we trace the extraordinary journey of Max Planck. It is important to recognize that every great discovery in science comes with challenges, doubts, and resistance. Planck's groundbreaking work on energy quanta and the foundations of quantum theory was no exception. While today we celebrate his achievements as revolutionary, during his lifetime he faced skepticism from peers, philosophical resistance, and the profound challenge of reconciling his radical ideas with his own respect for classical physics. Understanding these obstacles not only highlights the courage required for scientific innovation, but also illuminates the human side of Planck's intellectual journey. At the heart of the challenges Planck faced was the sheer radical nature of his hypothesis. When he proposed that energy is quantized discrete rather than continuous, it directly contradicted centuries of established scientific thought. Classical physics, grounded in the work of Newton, Maxwell, and the laws of thermodynamics, had successfully described the macroscopic world. Energy had always been assumed to flow smoothly and continuously. To suggest otherwise was seen as almost heretical by some physicists of the time. Planck himself initially treated the idea of quanta as a mathematical device rather than a fundamental principle, precisely because he understood the radical implications. His cautious approach reflects the intellectual tension he experienced, the excitement of discovery intertwined with the weight of challenging the scientific consensus. Skepticism came not only from a conceptual standpoint, but also from experimental limitations. The late 19th and early 20th centuries were a period of rapid scientific advancement, yet many experimental results were difficult to verify with precision. Some physicists questioned the validity of Planck's Blackbody radiation formula, suggesting that deviations between theory and experiment might indicate errors rather than a need to rethink fundamental assumptions. Planck's meticulousness helped him navigate these doubts, but the broader scientific community often reacted slowly to accept ideas that seemed so counterintuitive. Another challenge Planck faced was the philosophical resistance to abandoning determinism. Classical physics had provided a predictable, almost mechanical universe. If energy is quantized, if interactions at the microscopic level are discrete and probabilistic, the deterministic world view no longer holds. Many scientists struggled to reconcile this with their philosophical commitments. Planck himself respected the classical framework deeply and was initially cautious about asserting that quantization applied universally. This tension between revolutionary theory and philosophical tradition added an extra layer of difficulty to gaining acceptance. Moreover, Planck's work coincided with rapid scientific developments in Germany and Europe, which created an environment of both opportunity and competition. Physicists like Hermann von Helmholtz and others were making their own advances in thermodynamics and electromagnetism, and there was a natural skepticism toward radical departures from classical norms. Planck had to carefully demonstrate the mathematical and experimental rigor of his work, showing that quantization was not an arbitrary assumption, but a solution grounded in observable phenomena. This required patience, precision, and a willingness to defend his ideas against critical scrutiny, a process that could be personally and professionally taxing. Planck also faced the challenge of communicating a radical concept to a scientific community not yet ready for it. He had to present energy quanta as a formal hypothesis rather than an outright claim about nature. This careful, almost reluctant presentation may have delayed full recognition of his discovery, but it also reflected his humility and dedication to evidence-based reasoning. Planck's ability to balance innovation with caution demonstrates a rare intellectual discipline, introducing a revolutionary idea without forcing immediate acceptance, letting the data and logic convince others. Personal challenges compounded the professional ones. During his life, Planck experienced profound personal tragedies, including the deaths of his children and his wife, and the upheavals of World War I and the political turmoil in Germany. Yet he continued his work, maintaining focus on his scientific pursuits despite immense personal suffering. This resilience allowed him to advance physics in a time of great societal and personal uncertainty, demonstrating not just intellectual courage, but extraordinary human fortitude. Despite the initial skepticism, Planck gradually gained recognition as experimental evidence accumulated. Physicists such as Albert Einstein began to build upon his ideas, extending the concept of quanta to light and atomic theory. Yet even as his work gained acceptance, Planck remained deeply humble, often emphasizing that he was only a small part of a larger scientific process. This humility and integrity further strengthened the credibility of his ideas, enabling his contemporaries to embrace and expand upon the quantum framework. In retrospect, the challenges and skepticism Planck faced highlight the courage required to innovate. Introducing a concept that challenges centuries of established knowledge is never easy. It requires intellectual rigor, patience, and resilience in the face of doubt, qualities that Max Planck possessed in abundance. His ability to persist, reason carefully, and balance radical ideas with evidence-based caution allowed him not only to overcome these obstacles, but also to lay the foundation for an entirely new understanding of the universe. In conclusion, Max Planck's journey was marked by both brilliance and struggle. The skepticism he faced, from peers, philosophical traditions, and the constraints of experimental physics, underscores the revolutionary nature of his work. Yet, through meticulous reasoning, humility, and perseverance, Planck overcame these challenges, ultimately transforming physics forever. His experience reminds us that scientific breakthroughs are rarely immediate or easy. They demand courage, patience, and a steadfast commitment to truth. Planck's legacy is a testament to the power of perseverance in the face of doubt, showing that even the most revolutionary ideas can succeed when grounded in evidence, logic, and unwavering dedication. Recognition, awards, and the Nobel Prize, ladies and gentlemen, as we continue to trace the remarkable journey of Max Planck, it is essential to recognize that his groundbreaking contributions to physics were not only transformative in theory, but were eventually acknowledged with the highest honors in science. Planck's dedication, intellectual rigor, and perseverance culminated in a recognition that cemented his place in history: the Nobel Prize in Physics. His accolades are not just milestones of personal achievement. They reflect the global acknowledgement of the profound impact of his work on modern science. After publishing his revolutionary work on energy quanta in 1900, Planck's ideas initially faced skepticism, as we discussed previously. Many in the scientific community were hesitant to depart from the classical physics framework that had dominated for centuries. However, as experimental evidence accumulated, the validity and significance of Planck's work became increasingly clear. Experiments on Blackbody radiation, photoelectric effects, and atomic spectra began to confirm the revolutionary principles he had introduced. These confirmations elevated Planck from a highly respected theorist to a pioneer of a new era in physics. In recognition of his monumental contributions, Max Planck was awarded the Nobel Prize in Physics in 1918. The Nobel Committee specifically cited his discovery of energy quanta, acknowledging that his work had fundamentally altered the understanding of energy and matter. This accolade was especially significant because it represented a formal validation of an idea that had initially been met with doubt and skepticism. By awarding Planck the Nobel Prize, the scientific establishment recognized not only his specific achievements in resolving Blackbody radiation, but also the broader paradigm shift he initiated, which would come to define quantum physics. Beyond the Nobel Prize, Planck received numerous other honors and positions that reflected his standing in the scientific community. He was elected to the Prussian Academy of Sciences and became a leading figure in German and European physics. He held prestigious academic appointments, guiding students and influencing generations of physicists who would carry forward the principles of quantum theory. These roles allowed Planck not only to advance his own research, but also to mentor others, ensuring the continuation and expansion of the scientific revolution he had sparked. Planck's recognition was not limited to formal awards. He became an intellectual figure whose ideas were discussed and debated internationally. Correspondence with contemporaries such as Albert Einstein, Niels Bohr, and Erwin Schrödinger demonstrated the extent to which his work influenced cutting-edge research. While Planck himself remained humble, often emphasizing that science is a cumulative endeavor. The respect and admiration he commanded among his peers were unmistakable. He was regarded not only as a brilliant theorist, but also as a thoughtful, methodical, and principled scientist, qualities that enhanced the impact of his discoveries. The timing of Planck's recognition is also notable. By the time he received the Nobel Prize in 1918, quantum theory was already transforming the landscape of physics. Einstein had applied Planck's quantum hypothesis to light in his explanation of the photoelectric effect. Bohr was developing his atomic model based on quantized energy levels, and experimental evidence from atomic spectra and radiation studies was confirming the accuracy of the quantum framework. The Nobel Prize, therefore, was not simply a reward for solving a single problem. It was a recognition that Planck had initiated a revolution, creating tools and concepts that enabled others to unlock deeper truths about the universe. Planck's recognition also illustrates the interplay between patience and persistence in scientific achievement. His ideas were not immediately celebrated. Acceptance came slowly, as experiments and theoretical work gradually validated his hypotheses. The Nobel Prize and other accolades were the culmination of decades of careful thought, meticulous calculations, and courageous intellectual risk-taking. This serves as a powerful lesson for scientists and students alike. True innovation often requires enduring skepticism and maintaining commitment to the truth, even when immediate recognition seems elusive. Importantly, Planck's awards highlight the global significance of his contributions. While his work originated in Germany, the implications of quantum theory extended worldwide, influencing physics, chemistry, and even philosophy. Recognition by the Nobel Committee symbolized not only national or regional admiration, but also an acknowledgement by the international scientific community that Planck's discoveries had fundamentally changed humanity's understanding of nature. His legacy is therefore both personal and universal, a testament to the power of ideas that transcend borders. Even as he accumulated honors, Planck remained modest, consistently attributing his achievements to rigorous study, careful observation, and the collaborative progress of science. This humility enhanced his reputation and inspired confidence in his work, allowing his contemporaries to explore the revolutionary implications of quantization without resistance from the man who had introduced it. In this sense, Planck's recognition was not merely ceremonial. It reflected the moral authority and intellectual integrity he brought to the emerging field of quantum physics. In conclusion, Max Planck's recognition, awards, and the Nobel Prize in 1918 represent both a personal triumph and a historic acknowledgement of the birth of quantum theory. Through meticulous research, intellectual courage, and unwavering dedication, Planck transformed physics, challenged centuries of assumptions, and laid the foundation for technologies and theories that continue to shape our world. His accolades are a testament to the enduring power of insight, perseverance, and integrity, reminding us that revolutionary ideas, even when initially met with skepticism, can ultimately achieve recognition and reshape our understanding of the universe. Max Planck's journey from cautious theorist to globally recognized pioneer illustrates the profound rewards of scientific innovation. His legacy demonstrates that recognition in science is not merely a measure of personal achievement, but a reflection of the transformative impact of ideas on human knowledge and progress. In honoring Max Planck, the world celebrated not only a brilliant physicist, but also the birth of a new way of seeing and understanding the natural world. Planck's philosophical and scientific beliefs, ladies and gentlemen, as we explore the life and legacy of Max Planck, it becomes clear that his greatness was not only defined by his scientific discoveries, but also by his philosophical and scientific beliefs. Planck was a thinker who approached the natural world with deep humility, unwavering dedication, and a profound respect for both empirical evidence and the inherent order of the universe. Understanding his philosophy provides a window into the mindset that enabled him to make breakthroughs that would forever alter physics and our understanding of reality. At the core of Planck's scientific philosophy was a belief in the discoverable order of nature. Unlike some who saw science as a tool for mere prediction or technological gain, Planck viewed it as a means of understanding the fundamental principles governing the universe. He believed that laws of nature exist independently of human perception, and that it is the duty of the scientist to uncover these truths with careful observation, rigorous reasoning, and disciplined experimentation. This conviction drove Planck throughout his career, from his early studies in thermodynamics to his revolutionary work on quantum theory. Planck was also deeply committed to methodical reasoning and intellectual rigor. He approached problems with patience, meticulous calculation, and a step-by-step approach. Even when confronted with phenomena that seemed paradoxical, such as Blackbody radiation, he relied on logic and evidence rather than intuition or speculation. This methodical philosophy allowed Planck to introduce radical ideas like energy quanta, without abandoning the principles of careful, systematic investigation. In his work, we see a fusion of bold creativity and disciplined reasoning, a combination that underpinned all of his scientific achievements. Another central aspect of Planck's philosophy was humility before nature. He recognized the limits of human understanding and the provisional nature of scientific knowledge. Even after proposing the concept of energy quanta, Planck initially considered it a formal hypothesis, a mathematical device to solve a specific problem, rather than a definitive description of reality. This humility reflected his understanding that science is a continuous process. Discoveries are steps along an ongoing journey rather than absolute conclusions. It also illustrates his ethical approach to science, presenting revolutionary ideas cautiously, ensuring they could withstand scrutiny, and allowing the scientific method to guide their acceptance. Planck's philosophical beliefs were also intertwined with his views on determinism and order. He respected classical physics and the deterministic world, view it represented but recognized that at microscopic scales, nature exhibited a discrete and probabilistic character. Instead of rejecting classical principles outright, he sought to integrate new quantum insights with the broader framework of physics. This balance between tradition and innovation reflects a nuanced philosophical approach, one that values the coherence of scientific knowledge while remaining open to radical revisions when empirical evidence demands it. Religion and metaphysics also played a subtle role in Planck's world view. Planck was a man of deep moral and spiritual conviction, and he saw no conflict between his scientific work and his personal beliefs. He often remarked on the sense of order, harmony, and lawfulness in nature, viewing scientific discovery as a form of understanding the underlying rationality of the universe. This philosophical perspective reinforced his patience, integrity, and persistence in the face of skepticism and uncertainty, providing him with both intellectual and emotional grounding during the challenging periods of his life. Planck's beliefs also emphasized the social and ethical responsibilities of scientists. He understood that scientific knowledge has profound implications for society, and that discoveries must be pursued with integrity and a sense of responsibility. Even during turbulent times, including World War I and the political upheavals of Germany, Planck remained committed to advancing science ethically, fostering dialogue among peers, and defending the autonomy of research from political interference. His approach reflects a philosophy in which scientific progress is inseparable from moral responsibility. Another key element of Planck's philosophy was his faith in the cumulative nature of scientific knowledge. He did not view discoveries as solitary triumphs, but as contributions to a larger, ongoing enterprise. This belief is evident in his interactions with contemporaries like Einstein and Bohr, whom he encouraged, mentored, and supported. Planck saw science as a collaborative pursuit. Each generation builds upon the foundations laid by its predecessors, refining, challenging, and expanding the boundaries of understanding. His philosophical commitment to cumulative progress ensured that the quantum revolution would not end with him, but continue to evolve and transform the field. In essence, Planck's philosophical and scientific beliefs can be summarized as a commitment to truth, rigor, humility, ethical responsibility, and the orderly structure of nature. These beliefs shaped not only his scientific methodology, but also his interactions with the scientific community and the broader society. They allowed him to propose revolutionary ideas, such as energy quanta, with care and authority, ensuring that his work would endure scrutiny and eventually transform our understanding of the universe. In conclusion, Max Planck's philosophical and scientific beliefs were as essential to his legacy as his discoveries themselves. His deep respect for the order of nature, his disciplined approach to research, his humility, and his ethical commitment enabled him to navigate the challenges of pioneering quantum theory and inspired generations of physicists. By understanding his philosophy, we gain insight not only into the methods behind his scientific breakthroughs, but also into the character of a man whose ideas reshaped our perception of reality. Planck reminds us that science is not only a search for knowledge, but also a disciplined, ethical, and reflective engagement with the mysteries of the universe. Legacy of Max Planck in modern physics, ladies and gentlemen, as we reach the final keynote of our exploration into the life and work of Max Planck, we reflect on the enduring impact of his contributions, the legacy he left in modern physics. Planck is rightly called the father of quantum theory, but his legacy extends far beyond the concept of energy quanta. His discoveries, methods, and philosophical approach reshaped the entire landscape of physics and continue to influence science, technology, and our understanding of the universe today. Max Planck's most immediate and transformative legacy is the birth of quantum mechanics. By introducing the idea that energy is quantized, he laid the groundwork for the scientific revolution that would follow in the early 20th century. Physicists such as Albert Einstein, Niels Bohr, Werner Heisenberg, Erwin Schrödinger, and Paul Dirac built upon Planck's work, developing a comprehensive framework that explains the behavior of atoms, electrons, photons, and subatomic particles. Every major advance in quantum mechanics traces back to Planck's initial insight. Without his hypothesis of energy quanta, the photoelectric effect, atomic models, quantum statistics, and the development of particle physics would have been delayed or taken an entirely different trajectory. In this sense, Planck's legacy is not just historical. It is the foundation upon which modern physics stands. Another significant aspect of Planck's legacy is the universal constant he introduced, known as Planck's constant h. This fundamental constant is essential to nearly every equation in quantum mechanics. It establishes the scale at which quantum effects become significant, bridging the gap between classical and quantum physics. Today, Planck's constant is central to our understanding of energy, frequency, momentum, and even the uncertainty principle. It provides a concrete measure of the discreteness of energy and action in the universe, and underpins countless technological innovations, from semiconductors to lasers, and from nuclear magnetic resonance to quantum computing. Planck's constant is a symbol of the profound shift he initiated, representing both a practical tool and a conceptual revolution in science. Planck's influence also extends to the philosophy of science. He demonstrated that revolutionary ideas could coexist with intellectual rigor, careful observation, and ethical responsibility. His methodical approach, balancing caution with boldness, has inspired generations of scientists to pursue innovation grounded in evidence. He showed that scientific breakthroughs often emerge slowly, requiring patience, persistence, and humility. In modern physics, this philosophy continues to guide research in complex fields such as particle physics, cosmology, and quantum information theory, where the boundaries of knowledge are constantly being tested. Planck's example reminds scientists that curiosity and discipline are equally important in the pursuit of discovery. Another dimension of Planck's legacy is his impact on the scientific community and institutions. Beyond his research, he played a crucial role in fostering collaboration, mentoring young physicists, and promoting scientific communication. He held prestigious positions in the Prussian Academy of Sciences, contributed to scientific societies, and encouraged international dialogue among physicists. By nurturing the next generation and promoting rigorous standards, Planck ensured that quantum theory would not only survive but flourish. His influence on the culture of physics is still felt today, as institutions continue to uphold the values of integrity, collaboration, and meticulous inquiry that Planck championed. Planck's legacy also touches the technological world. Quantum mechanics, built upon his initial discoveries, has led to innovations that define modern life. Transistors, lasers, MRI machines, and computers all rely on principles derived from quantum theory. The rise of quantum computing and quantum cryptography, poised to revolutionize information technology, can also trace their conceptual origins back to Planck's work. In this way, Planck's ideas bridge the abstract and the practical, demonstrating that foundational science can transform the material world in profound ways. Furthermore, Planck's intellectual courage and philosophical insight continue to inspire scientists and thinkers beyond physics. His willingness to question long-held assumptions, embrace uncertainty, and propose radical ideas while respecting evidence sets a standard for innovation in all fields. Philosophers of science, mathematicians, and engineers alike have drawn lessons from his career, understanding that progress often requires a balance of imagination, logic, and integrity. Planck's life exemplifies the interplay between personal virtue and professional achievement, a model for anyone seeking to expand the frontiers of human knowledge. Max Planck's legacy is also timeless because it represents a bridge between centuries of physics. Classical physics, from Newtonian mechanics to Maxwellian electromagnetism, provided the foundation, but Planck's insights opened the door to the 20th century's quantum revolution. His work connects our understanding of the macroscopic world with the mysteries of the microscopic universe. It has influenced everything from atomic theory to quantum field theory, and the ongoing exploration of fundamental particles and forces in the universe. In this sense, his legacy is not just historical. It is a living framework that continues to shape contemporary physics. In conclusion, the legacy of Max Planck in modern physics is profound, multifaceted, and enduring. He gave the world quantum theory, introduced Planck's constant, and inspired a philosophical approach to science rooted in rigor, humility, and ethical responsibility. His work enabled technological innovations that define modern society, shaped the next generations of physicists, and transformed our understanding of the universe. Planck's insights remind us that scientific revolutions are not merely about formulas or experiments. They are about changing the way we perceive reality itself. Max Planck's legacy is a testament to the power of curiosity, discipline, and courage. By daring to question classical assumptions and proposing a radical new vision of energy and matter, he reshaped science forever. Today, in every quantum calculation, in every laser, in every computer chip, and in every experiment probing the mysteries of the universe, we see the enduring influence of Max Planck, the father of quantum theory. His life and work stand as a beacon for all who seek to explore, understand, and innovate in the endless frontier of science.